So in the previous video, we introduced the concept of the noble gas configuration, the noble gas electron configuration that we can use for atoms and writing their electron configurations. In that noble gas configuration, we put the closest previous noble gas in brackets, and then the rest of the electron configuration is how you would normally write it for the expanded or full electron configuration. This slide points to 2 points and a trend from the periodic table that we can use to help us with determining something called the number of valence electrons for an atom, specifically for an atom that is in a main group in the periodic table. So in groups 1 through 8A, with the exception of helium and omitting the middle transition metals. Looking at the condensed or noble gas configurations for main group elements, some of which are shown here, you see that all elements in the same group, they have different noble gas elements in brackets, but they have the same number of outer shell electrons. Those outer shell electrons, those electrons that are beyond the core electrons that we identified within the noble gas configuration, those electrons are called valence electrons. And valence electrons are super important because it is those electrons that are available and accessible for bonding. And so in subsequent chapters, when we start talking about atoms and how and why they combine in certain ways to form chemical bonds, we're going to need to talk about valence electrons and know how many valence electrons a particular element has. The number of valence electrons for a main group element can easily be determined from the condensed electron configuration because it's the number of outer shell electrons. And for main group elements, it happens to be equal to the group number. So all the elements in group 1A, they all have one valence electron. Elements in group 2, they all have 2 valence electrons. The exceptions, the one exception shown here is helium. Helium is a noble gas, it's in group 8A, but it has 2 valence electrons. And we are skipping the transition metals because they do not follow this trend. So that is a periodic trend that you should know and you'll be using in subsequent chapters, that for main group elements, the number of valence electrons is equal to the group number. And the definition of a valence electron is an electron that is in the outer shell of the atom. It's beyond the core electrons, and it is those atoms that are involved in bonding. So before we move on from this concept of electron configurations, let's go ahead and visit a few anomalies or exceptions of electron configurations that are seen in the periodic table. Now those exceptions, and there are a few of them, they are mainly found in the transition metals. And I'm not going to expect you to memorize all of them. The two that I want you to be familiar with, I have here in this slide, chromium and copper, because these anomalies, I think, speak to an important characteristic about atomic orbitals that we will revisit later in the course. But let's say I was to ask you to give me the condensed electron configuration for chromium. Well, based off of all of the rules that we've talked about so far, you would say that that condensed electron configuration, the closest previous noble gas, is argon, 4s2, 3d4. Well, it turns out that if you look it up in your chemistry book, or in any chemistry book, do experiments, it turns out the actual observed electron configuration that fits Schrodinger's equation and all that, the actual electron configuration isn't 4s2, but it's 4s1, 3d5. So one of those electrons from the 4s orbital got transferred to the 3d orbital. If I was to ask you for the electron configuration for copper, you would think, from all the rules we have talked about so far, that that configuration would be argon, closest previous noble gas, 4s2, 3d9. But instead, you would find in your chemistry book or in MindTap or in any chemistry book that instead of 2 4s electrons again, we have 1 4s electron and 10 3d electrons. So what is up with that? Why in these two elements is one valence electron transferred to the next 3d orbital? Well, we can kind of explain that if we would look at the orbital diagrams for chromium and for copper, specifically using the abbreviated electron configuration and using the expected electron using the electron configuration that is actually seen. If I was to write an orbital diagram for the abbreviated electron configuration of chromium, argon 4s1 3d5, I see that in this situation, all of my 3d orbitals are half filled. Before, if I was to keep with the 3d4, not all of my 3d orbitals would be half filled. I'd have 2 electrons in my 4s orbital. Similarly with copper, when I write that electron configuration with what is actually seen, 4s1 3d10, I see with that electron configuration, by taking that 4s orbital or 4s electron and putting it in the 3d orbital, all of my 3d orbitals are filled. That would not have happened if I had just 4s2 3d9. So I pick these two examples for anomalies in electron configurations to share with you because it speaks to an important concept that there is something very stable about having half-filled or all-filled subshells, specifically d orbitals, for those transition metals. And having my 3d orbitals half-filled or all-filled explains why we see these anomalous electron configurations for chromium and copper. And so, like I said, there are a few other transition metals that do that. I'm not expecting you to memorize them. These are the two that you need to be familiar with for your exam. But you should know that there are some anomalies, some exceptions of electron configurations in the periodic table. 2 of them are chromium and copper. You should know what their electron configurations are and be able to explain why those electron configurations are what they are and why they are different from the previous rules that we have talked about.